This is a profoundly important project for all of us during this pandemic time. You can build it on your own and you can deploy it. That way it is very important. Otherwise, it's a very small project. Once you understand the intricacies of it, you will be able to do it. Well, this is a temperature pulse oximeter. Normally, the oximeters you find in the market, which is available for around 1500 to 2000 INR. But actually, it costs far less than that. And how it works is also very important to understand. Well, I am S. Bera. I have more than 100 DIY projects appeared in India and other countries like UK, USA, Russia, Europe, and Australia. And before that, one more project that was a jumbo sanitizer that also appeared in many places there. I also am a blog writer. I have written more than 200 blogs, appeared in various magazines, newspapers, and some of my company in-house journals. Well, friends, I dedicate this to my dear mom. Well, there are a lot of cheap oximeters available in the market for INR 2000 or less. And these are built on Chinese MAX 30100 or 102 pulse oximeter sensors. Those are available in Indian suppliers also for as low as INR 250. Yet there is no hobby project for temperature pulse oximeter combined. You see those meters, they grip your finger. They can easily measure temperature, but they don't. They measure only your oxygen level and your pulse level. MAX 30100 is an infrared measuring device. To be precise, along with infrared, it also emits a red light. Well, what happens, this oxygenated blood, it takes more IR light. It absorbs IR light and passes the red light. And whereas the deoxygenated blood, it absorbs more red light and passes infrared light. So the sensors, what it does, it sends a IR light and a red light, and it measures back the reflected energy level. And that's the measurement of the oxygen level of your blood. And the pulses through which it measures between oxygenation and deoxygenated, that's the measurement of your pulse. So you tell your computer to count all those gaps and it will do it like a dedicated slave, and that's the project. Well, for MCU, this is an I2C device. And for I2C device, there is an important design consideration for pull-up. It creates an LC circuit. The inductance or conductance resonance circuit it creates, which actually helps the I2C to work properly. And this thing comes into being when you start that where.begin. That in the Arduino you start where.begin, and it starts working that way. And an incorrect pull-up will give wrong signal output. Okay. Now this MAX 30100, these are all flooded in the market. They have some distinct errors, and that's why will not be able to make your oximeter works perfectly okay for you. One is that for MAX 30100 to work perfectly, there are two voltages are required. One is the 3.3 volt for lighting those IR LED and normal red LED to on, and 1.8 volt for the signal. For measurement of that feeble weak signal, 1.8 volt is used. If you use more voltage, then what will happen? It will create so much noise that the measurement will be problematic. So these two voltages are required. But now the thing is that for this machine to work with a popular I2C model, you need a pull-up from 3.3 volt. If the machine operates at 3.3 volt, or from 5 volt if it operates from 5 volt. And the problem lies there. This Max 30100, this Chinese made machines, what they did is, see, it's an I2C design. There are V-in, SCL, SDA, and there is one interrupter, IRD, RD, and GND. IRD and RD, these are the LEDs. But problem is that interrupter you have not used. SCL and SDA and interrupter, they all three have pull-up resistors. And if you see the right picture clearly, those are three pull-up resistors, and those three are connected to 1.8 volt. So probably Chinese makers, they made this design for a particular MCU, which we really don't know. But they have flooded the market with this cheap sensor. So as a result, what happens? We end up buying these sensors and we do not know which sensor it works perfectly okay. And we try to do it with Arduino and we find that we are not getting the proper results. And one more problem is there. Some of the Chinese models, there are two regulators are here. One is that 6-pin regulator, that is a V into 5 volt, and this 3-pin 65K9, this is a 1.8 volt regulator. Some of the Chinese designer, instead of 1.8 volt, they have put a 2.8 volt. So with the 2.8 volt regulator, where the 2.8 volt is used as a sensor design, control, sensor measurement, I really don't know how the two voltages, that 5 volt and 1.8 volt, this point is measuring 1.8 volt, or this resistor, top of this resistor is measuring 1.8 volt, then anyway, one way this is all right. Now we have to do some rigging work here. What you have to do, either you remove all these three resistors, and put three new resistors, 4.7K to the 3.3 volt pull up, or you cut this small line here. That cut is written there. You cut that line here and put a jump wire here. This is the jump wire from the top of this resistor up to the opposite middle line of this 1.8 volt regulator. If you see clearly, closely here, I did exactly the same thing. Exactly the same thing from the top of this resistor, which is the common pull-up, going to 1.8 volt. I cut the track below and connected it here. And this is the jump wire I have used. If you can do it now, it is absolutely all right to give you correct reading. Ignore this push button. Ignore this push button. This is not a part of this project. And if you do not do this rigging, then what will happen? You will find that sensor is installed successfully. It is diagnosed by Arduino successfully. Yet the readings are horribly wrong. If you cross-check with a pulse oximeter, you will find that readings are horribly wrong, yet the Arduino is working perfectly all right. That's one point. If you connect a digital temperature to another GPIO of your microprocessor, it will not work in tandem with Max 30100. That is another problem. Now, third thing, we thought that we actually did this project for some of our high-skilled operators who came from outside, and after a true nut checking, they were deployed for work. Of course, after being negative, they are deployed for work. And there we thought of putting this backpack on their wrist so that we'll be able to continuously monitor their oxygen and pulse and temperature. And again, the next challenge was making it portable with long-lasting battery operation. So let's, we have addressed all those points. Let's see. One is that for a microprocessor, we used ESP32. ESP32 is a 160 megahertz dual core, yet one of the cheapest microprocessor, yet very powerful microprocessor. available in the market. It is available for as low as 500 rupees nowadays. And in international market, we will get it for $4 to $5. We have provided multiple networks, as many as you can provide with ID and password to the sketch, and it will try all those networks, and whatever is giving you the first come first serve means the first one it will get connected. And we have also provided a lot of checks there. If the network is connected but network is not able to transfer data from the buffer to the internet, then again it will go and try for the next network. So that way a lot of built-in intelligences are provided there. It measures temperature and then collects a number of pulse and oximeter reading till it becomes stabilizes. In a rapid succession, it will take 20 readings, and when it becomes stable, the readings are stabilized, you find that it is at par with a oximeter reading, then it will upload data to thingspeak.com cloud server. Well, nowadays that creating an account in ThinkSpeak and then uploading data in ThinkSpeak, it's very easy. You can do it jolly well. Only thing, when you open an account, you will get a write key, permission to write data into ThinkSpeak via a key. You have to note down that key and you have to deliver that key in the Arduino sketch. Then you are done for. Data will continuously be uploaded to your thingspeak.com web page, your personalized web page, and you will be able to create a lot of trending and everything. You can do it. Well, after uploading data to ThinkSpeak, ESP32 and Max30100 goes to deep sleep mode for 20 seconds to save battery. After that, the ESP32 wakes up again and continues. During the entire this life cycle, it takes 160 milliampere current on 3.3 volt for 4 to 5 seconds to upload data. And then it goes back to 4.2 milliampere for 16 seconds. So that's why how it works. And it saves a lot of power on a 18650 battery. On a 18650 battery, normally, which it looks like this, which it looks like 18650 battery, it runs for at least 1 week. It will run comfortably, and if not 2-3 weeks. This is the schematic I have drawn for you. It's a very simple schematic. The DS18B20 is the digital temperature sensor. This is a Dallas semiconductor. It's a very precise. You can set it to measure temperature up to 4 decimal. Yes, I repeat, 4 decimal. Up to 4 decimal, you can take correct reading from minus 50 degree to up to 150 degrees centigrade. A very wide, versatile digital temperature sensor. It measures data, then it ESP32 connects to internet, and then ESP32 reads the oximeter data. All these pins are not used. All these pins are not used at all. Only SCL, SDA, and VIN and GND. These 4 pins are used. And after uploading the data, after successfully uploading the data, this LED will blink for a moment, saying that, indicating that the data has been uploaded. And then you can see the data is continuously being stacked up in your thingspeak.com web page. Well, this is the prototype. The battery will be placed on the front gap portion, and the temperature probe pulse oximeter sensor Max30100, those are placed side by side. When you place your finger or your wrist onto it, it will measure the both. It will measure the both. It will put in a comma. It will put in a comma separated value string, and then it will upload to thingspeak.com in one go. In one go, it will pump all those data into the cloud server. So these are the checks, because the things completely happens behind your back, and uh, in the attached probe of the object, and you cannot monitor it perfectly and every time. So we have provided few checks there. One is that in case the probe does not get signal, it does not get internet signal, Wi-Fi signal. It will happen. What happen if you have a campus Wi-Fi? It will work very well, jolly well. We have a campus Wi-Fi here, so everywhere it finds internet connectivity. So in case the probe does not get signal, it hangs. In this condition, the ESP32 will start counting, and after 25 seconds, it will restart on its own, and it will try the next. In case the uploading to thingspeak.com fails, the ESP32 will restart on its own. Hence, it's uploading to ThinkSpeak is nothing like you open the ThinkSpeak server and you will write that line in the browser page itself with that right key put in between. And if you press that enter button, the data will go to ThinkSpeak. Exactly the same thing is done inside ESP32. So in case it fails, it finds that internet is not working, whatsoever it is, it will restart again. So on a LiPo 26650 or 16650, it will work for weeks. 16650 is a bigger battery. It looks like this. It looks like this. This is slightly bigger and thicker. It will work for weeks after weeks on this battery. It is very big, very thick. It is 4 ampere hour battery. 4 ampere hour. An LED is provided with which will bring for a brief period to indicate successfully uploaded to the cloud. And you can reduce the power consumption further down by removing the extra LED that glows continuously on the ESP32. If you use the development board, and if you use a bare minimum ESP32, you can reduce the power consumption further. That was about that project, the schematics, and those things. And before coming to that question session, I will show you the sketch, little bit of that sketch. Well, this is the sketch. If you can see it here, I have provided a number of ID passwords. So all these ID password, it will connect one after another. And if it fails at any point of time, it will restart. And these are the restart command. These are again one more restart command. And in the loop session, it measures the temperature first, then it measures the oxygen and pulse measurement it does. It goes to the serial pin, but we are not having any serial pin connected in the actual field usage. And this uploads data. When the 15 number of 15 to 20 number of data, when it is collected, then it uploads. This is the upload command, and upload is here. It takes all the data at a time and pumps it back to ThinkSpeak. And if the ThinkSpeak does not respond properly, it will restart again. Here is the deep sleep, and if it fails to connect, it will restart again. And this is the deep sleep mode of our pulse oximeter. Well, that was all about this small project.
Thank you, sir.
Okay, Asini, thank you.
Thanks everyone for being here.